In our previous tutorials, we looked at L-section matching, and we saw how this is a very simple way to match two resistive terminations that can be applied in most cases. We'll see in due course how this technique can also be applied to complex terminations, but for now we'll stick with just having a resistive load and a resistive source. The problem with L-section matching, as we've seen before, is that the load and source impedances determine largely what Q our network is going to have. Remember that, as we've seen, a matching network behaves effectively like a filter. And whereas with L-sections we don't have a great deal of control over the bandwidth of the filter and the sharpness of the response, there are other type of networks that allow us to carry out a design with the specific frequency response that we would like our matching network to have in mind. So, for example, we could design a network with a specific Q so as to have the required selectivity around the frequency band that we are operating and to reject unwanted signals very effectively. Now, how do we design a matching network with a specific Q in mind using the Smith chart? First of all, let's represent points that have different impedances but identical Q on the Smith chart. Let's go to Project Options, select our frequency of operation, we'll keep it to 1 GHz for consistency, click on Apply, then check our global units. We use millisiemens for conductance, nanohenries for inductance, and for capacitance, as usual, we'll pick picofarads. Then let's open a new schematic and let's call it QDemo. Then we'll make up a very simple network which will allow us to represent a complex impedance of the Smith chart. So let's just press Ctrl P first to be able to get a measurement port, and then let's press Ctrl L to fetch an element which allows us to represent a complex impedance called imped. Let's add a ground reference by using Ctrl G, and then connect the two elements together. Now, I am not going to assign values to the resistance and the reactance of our imped element directly, but I'm going to use an equation. To get an equation, all we need to do is just click on the equation icon up here, and then click to place it on the schematic, and then we can just type the equation in here. Say K equals 1. K would be the variable that we'd be using to assign values to our element imped. Bear in mind that in Microwave Office the name of variables is case sensitive, so make sure that you remember that. So first of all, let's set up an impedance here which has got exactly the same real and the same imaginary part. So we'll set the resistance equal to K and also the reactance equal to K. Of course, this impedance will have a Q of 1 because the ratio of the reactive over the resistive part is equal to 1. The other thing that we would like to do is to sweep the variable K across a wide range of values. So we can create a number of impedances which have all got the same Q, but of course they are all a different value. We can do this quite easily in Microwave Office by using a swept variable block. We can fetch it by pressing Ctrl L and then typing in VAR in the search box. Then we can place the block on the schematic like so. And we need to do two things. First of all, we need to assign it to a variable that's already on the schematic. And we've got one, which is K. So we must double click on here, and in between the quotes we'll have to put the name of the variable, which is K. Then we have to assign a range of values to this variable K. To do this, we just double click on values, and then in between the curly brackets we could just list a number of values that we want. But in this case I want very many values, and hence it's easier to use a different way to create an array of values. And that is just by typing stepped, and then we can give stepped 3 parameters. The starting point, which we'll say is 0, the end point, which we'll say is 1000, representing 1000 ohms in this case, and then the step, which is 1. So this way we're creating 1001 values for our resistance and reactance that we can let imped assume and then we will represent impedance on a Smith chart so that we can see how impedances which have different values but the same Q appear on the chart itself. So we're all ready to roll. We just need to right click on graphs now and then select new graph. We'll select a Smith chart as the type and we'll call it again QDemo. Now we right click on the chart and add a new measurement. Of course our measurement as usual is the S11. And in terms of the data source name, in this case we'll specify it and we'll say that it's our QDemo schematic. Now you can see that there are a couple of extra boxes here. First of all, we are asked what to use our sweep frequency for, but we've only got one frequency, so we don't have to worry about that. We could just leave it to what it is. And then MicroOffice is asking us, what do you want to do with the data that comes from your swept variable? And we want to plot all traces, because we want to plot all the S11 values for each impedance value that imped assumes, and hence we'll just keep this box to what it is. Now click on Apply and then OK. Then simulate. Now you can see how our points, which have all got a Q equal to 1, have described an arc on the Smith chart. So it is a very clear curve which describes points of equal Q. Now, if we go back to our schematic, what we can do is work out what curves we'll get as we increase the value of Q. To do this, I'm just going to use a very simple and crude technique. I'm just going to drag the mouse and select the whole circuit here, and then press Ctrl-C and Ctrl-V to create two copies of it. Notice how the port numbers have been automatically changed, and the same is applicable to the imped ID. You can see that now we've got port 2 and port 3, and the imped IDs as well have been changed to Z2 and Z3. What I'm going to do is simply multiply the reactance part of this imped element by different constants, so as to obtain a different value of Q. So we'll say that the reactance for this element is 2 times K, and then for this other element we can say that the reactance is 5K. And this will give us Qs of 2 and 5 respectively. Now if we go back to our graph, we of course have to add additional measurements here to be able to display this new graphs. So we just right click on the graph, go on to add a new measurement, and now all we need to do is basically get the reflection coefficients for the two extra networks that we've added. Now the second network that we've added has got 2 as an index for its port, so its reflection coefficient will be S22. Click on Apply, and then we'll also need to get a reflection coefficient for the third network, and the index for that port is 3. So it'll be S33 that we're looking for. Click on Apply and then OK. Now let's simulate. Now you can see that the arches increase in height as the Q is increased. So we are effectively describing this sort of lines on the Smith chart as we look at impedances with identical Q, and these arches, these lines, tend to go higher and higher as the Q of the impedances gets higher. The other thing that I'd like to point out is that so far I've been looking at impedances which have a positive reactance, and because of that all my arches are in the top half of the impedance chart, which as we know only has impedances with positive reactances. However, I would have similar curves if I went for negative reactances. So I can just verify this and go back to the schematic, and now all I can do is simply change the sign of the reactance for each element here so as to end up in the bottom half of the chart and verify that I get exactly the same curves. So if I just click on Simulate Now and then go back to the chart, you can see that you get exactly the same curves, but they're basically the mirror image with the x-axis as an axis of symmetry. Now you may ask, well, how do I draw these lines of constant Q? Do I have to go through this procedure every time? Well, the answer is simply that you don't. because Microwave Office helps you out in this particular respect, and you can plot lines of constant Q on your Smith chart very, very easily. So we just right click on the chart, select add a new measurement, and then under the linear measurement types you choose circle, and under the circle you can see that you've got an element called QCont, and the description reads constant Q contour. So you can see that here you've got the value of Q that you want to display the contour for, and this value could be anything. It doesn't have to be an integer number, it could be absolutely anything that you wish. And for example, now we can plot the same contours that we've actually worked out ourselves in a different way with the swept variable. So let's say that we want to plot the Q contour for Q equal 1. So we just type 1 in the box and then click on apply. And then we can plot the contour for 2 and click on apply, and decide to plot the contour for 5 and then click on apply and then OK. But you can say, well, I can't see anything else on there. Well, the simple thing is that because this is considered as a measurement, you have to simulate to be able to see it. So if we just simulate now, you can see that you've got your Q contours both on the top half of the chart and on the bottom half of the chart. You can see how they kind of overlap the ones that we worked out ourselves. So now let's get rid of all this stuff and get to work on designing networks which allow us to choose the actual Q. So let's delete the schematic here, and then also let's delete the graph here. So we're starting again from a blank canvas. So as we mentioned in the manual, you can use networks which comprise of 3 elements instead of 2 to be able to choose the Q of your matching network. 2 of the most common types are T and pi matching networks. Let's start with T matching networks. So let's open a new schematic and we'll call it Tmatch. And then as usual, we'll insert a measurement port by pressing Ctrl P, and we'll leave its impedance to 50 ohms. So our source impedance is 50 ohm. Then we'll add our resistor to the schematic by pressing Ctrl L and typing in RES, and give it a value of 10 ohms. Then we press Ctrl G, add a ground reference there, and then connect the port to the load. So we are once again looking at the case where we have a source and a load impedance which are both resistive, and the source impedance is greater in value than the load impedance. Let us also assume that the Q that we want to achieve for a matching network is equal to 5. So first things first, let's set up a graph. Of course, we'll choose a Smith chart as a type. We'll call it Tmatch. And then we need to set up a measurement that allows us to see the impedance from port 1. And that's, of course, an S11 measurement. So we go to the linear measurements under port parameters, then S, and we'll choose S11. Click on apply, and then OK. Then simulate. You can see that we are at this point along the chart. We can use the marker by pressing Ctrl M and then clicking on the point of interest to read the impedance that we see at that point. In fact, we may want to denormalize that impedance to make life slightly easier for us. Let's just right click, go on to properties, and then on the markers tab, let's choose to have the Z or Y display denormalized to 50 ohms, which is our source impedance. Click on apply, and then OK. So we've got an impedance of 10 ohms, and we want to get to an impedance of 50 ohms, which is right in the center here. We've seen how this can be accomplished quite easily by having both the impedance and the admittance charts displayed, and then by using an element in parallel and an element in series to get to the desired point. In this case, we want to accomplish our match by using 3 elements, which adds some complication but allows us to choose the Q. Some of these elements will be in parallel, some of these elements will be in series. So yet again, we have to do a little bit of work on the graphical aspects of a Smith chart so as to allow us to work things out in a relatively easy way. So let's just right click on the chart, go on to properties, and then on the grid tab, we'll decide to display both the impedance and the admittance grid, but not the values, because we said that can get a little bit too busy. We'll also choose the contour density to be coarse, again to increase legibility. And then on the Format tab, we'll choose the impedance lines to be green and the admittance lines to be red, so we can distinguish better between them. Click on Apply and then OK. And this now will look familiar to you because this is how we usually represent our Smith chart in our tutorials. The Smith chart that has got both impedance and admittance coordinates. Now, because we need to choose the Q this time, we need to have the Q contour for the desired Q displayed on the chart. And we do this, as we saw earlier, by right-clicking, going on to Add a New Measurement, selecting Circle under the Linear Measurements, then Q contour, and then we'll choose a value for Q of 5, which is our design goal. Click on Apply and then OK. Then we need to simulate for this to be displayed. And there we have it. We've got our contour displayed on the chart in purple. So the rules that apply are very similar to what we've seen before. Of course, when we add a capacitor in shunt, for example, we'll be moving down a constant conductance circle. When we add a capacitor in series, we will be moving down a constant resistance circle. And similarly, when we add a shunt inductor, we will be moving up a constant conductance circle. And when we add a series inductor, we will be moving up a constant resistance circle. So these rules, of course, still apply. The only thing is, this time we'll have to do this 3 times because we are using 3 elements. Now, you saw how between the 2 branches of the L-section matching, we got to an interim impedance. We first used one element to move to an interim point on the chart, and then from that point we move to our final point. In this case, what we want to do is to have one of those points, and there will be 2, to actually be on the constant Q contour. So effectively, in this case, because we'll have 3 branches, there will be 2 points which are interim points. So points that we are using along the path to get to the final destination. And one of these points should be on the Q contour. So remember that this is your initial point, and this is the point that you want to get to. So this is your starting point, and this is your destination. Now, if you want to use a path which includes an impedance point, which is on the Q contour, in this case, you can just move up the constant resistance circle shown here, up to this point up here. And of course, moving up a constant resistance circle means adding a series inductor. So we can add a series inductor to move from here to this point up here. So what is the reactance at my current point? My reactance is, of course, 0 as the marker shows. Then if I go up to this point here and hover over with the mouse and look at the readout at the bottom, I get about 49 ohms. So the difference in reactance between the point that I want to get to and the point that I'm at is around 49 ohms. This translates roughly into a value for our inductor of around 7.8 nanohenries. So what I can do is go back to my schematic and then press Ctrl L, get myself an inductor, and then I can place it in series with my load resistor and give it a value of 7.8 nanohenries. Then click on Simulate and have a look at the graph. And you can see that now I've moved to this point up here, which is just where I want it to be. Now remember that your final destination is the center of the chart. How do we get there now with 2 elements? Well, there's a number of ways to get there. For example, we can go down this constant conductance circle up until the point where we meet the unity resistance circle and then move down that way. Or we can just get ourselves all the way down to this other intersection with the unity resistance circle and then move up the circle to the center of the chart. Of course, depending on how you do it, you will be getting different elements. So the way we will do it is to go down the constant conductance circle up to the second intersection with the unity resistance circle, and then we will move up this unity resistance circle to the center of the chart. Because we are adding an element in shunt to be able to do this, we are moving down a constant conductance circle, so we are adding a capacitor in shunt, we need to change the marker readout to admittance to make our life a little bit easier. So right click, go on to properties, and then onto the markers tab, and choose the readout to be in terms of admittance. Click on apply and OK. So at this point here, the susceptance is about minus 19.6 millisiemens. And we want to get down to this point here, where the susceptance is around 8 millisiemens. I am moving to a point with a susceptance of 8 millisiemens, and I'm starting from a point of susceptance equal to minus 19.6. This susceptance is positive and works out to be 27.6 millisiemens approximately, and it corresponds to a value for the capacitor of about 4.4 picofarads. So yet again we can go back to our schematic and add this element here. So we'll press Ctrl L, fetch a capacitor, and then place it on the schematic like so, and then assign a value to it of 4.4 picofarads, and then simulate. If we go back to our graph now, we can see that we are exactly at the point where we want it to be, where the susceptance is around 8 millisiemens. Now, on the last leg of our journey, we want to move up a constant resistance circle to the center of the chart to achieve the match. To do this, first of all, because we are adding an element in a series, we need to change the marker readout to impedance. Click on apply and then OK. And then we'll have to have a look at the difference in reactance between our target point, which is the center of the chart and hence has a reactance of 0 ohms, and the point where we're at now, which has got a reactance of about minus 99.6 ohms. So the difference in reactance here is of course 99.6 ohms. This is positive and it corresponds to a series inductor being added. And the value of this inductor, the value that corresponds to this difference in reactance, is 15.9 nanohenries approximately. So now I can go back to my schematic and then make a little bit of space here and insert an inductor in series with the other bit of the network which I've already worked out, and assign a value to it which is the one we've just calculated, 15.9 nanohenries. And now click on Simulate, and then look at the graph again. And now we are bang on in the middle of the chart. Of course there is a slight error there, we're not exactly on 50 ohms, but we are very close. And this is the point where usually you would probably use the optimizer and to then really optimize the match to get to an exact 50 ohm. So I have fulfilled my design goal to have a matching network with a Q of 5. However, make no mistake here, although the Q of the network is 5 and this value is determined by the Q of the branch of the matching network which touched the constant Q contour, the loaded Q of the circuit will be different and somewhat lower. In fact, it will probably be overall just over half that of the network. This is very much the same as we had with L-section matching. Remember that in that case we calculated Qn, which was the Q of the branch where the resistive load was, and then we halved that value, the value of Qn, to get ourselves the loaded Q value. And the loaded Q value was that we calculated algebraically was very similar to the one that we saw from the frequency response. Why don't we just do that here as well and have a look at the frequency response of this network? Well, we saw how to do this in the previous case. We have to set up an S21 measurement. In order to set up an S21 measurement, we need to replace this load resistor with a port which has got an identical resistance to that of the load. So our load was 10 ohms. The impedance of our second port will also be 10 ohms. Then we need to, of course, add a ground reference down here. And now if we set up an S21 measurement, we can see what frequency response this network has. So let's do just that, and right-click on Graphs, choose New Graph. This time we'll choose a rectangular graph, and then we'll call it Tmatch versus frequency. So if we right-click on the graph now and go to add a new measurement, we can select again port parameters, S parameters, and then S21. Then what we can also do is select the dB box, because this will give us a better representation of the gain or attenuation of the network, and it is the usual way that this S parameter is displayed. So click on apply and then OK. Now the other thing that we want to do is see this frequency response across a broader frequency range. At the moment we've only got one frequency point, which is 1 gigahertz. So what we need to do is go to Project Options and then to the Frequencies tab, deselect the single point, and then change the units to megahertz, and select a start of 100 megahertz, a stop of 4000 megahertz, and a step of 1 megahertz as we did before. Click on Apply and then OK. Then simulate. Now you can see the frequency response of the filter here. It is somewhat still a sort of low pass, but not quite, because you can see that there is some attenuation at the lower frequencies as well. So we sort of have a passband effect, but a very asymmetrical one. Now what we can do, as we did before, is right-click on the graph, go on to Properties, and then on the Axis tab, select Logarithmic Scale. We can then click on Apply and then OK. And this gives us a clearer representation of the frequency response, a more classical one. Now I want to work out the 3 dB bandwidth of this matching network, which is effectively a filter. So what I'll do first is to zoom in onto the bit that I'm interested in. So I just want to zoom in on this hump here. And then I'm going to add a marker here by pressing Ctrl M and then clicking on the curve to be able to find the points where the frequency response is equal to -3 dB. So where the S21 is equal to -3 dB. So I can just move my cursor until I get to that point. This will do. So we get our first frequency point, the one on the right-hand side of the center frequency, which is equal to about 1132 megahertz. Then I can move the marker to the left-hand side of the frequency, of the center frequency, and I can find a similar point. So we can get to this point, which should do pretty well. And we can see that we get a frequency of about 772 megahertz. Let's go back to full display by pressing the View All button. So this gives us a Q, simply calculated from the graph, a loaded Q of about 1000 over 360, which is roughly 2.8. So really, although we designed our network to have a Q of 5 as a matching network, the loaded Q, which includes the terminating impedances, is much lower, and it is more or less half the value of the Q of the network which we've designed. And this is also the case, as we've seen, with L-section matching. Now, how does this frequency response compare to the frequency response of an L-section matching? Well, we had an example from another tutorial where we had a source impedance of 50 ohms and a load impedance of 20 ohms. So what we can do is devise a T-section matching for an identical network and then compare the two frequency responses. Now the procedure is very, very similar, and in a Blue Peter style I can just come up with one that I made earlier. So let's modify the schematic to have a load impedance of 20 ohms, which is exactly the one that we had for our L-section matching example. And then we need to change the values of our inductors and capacitor to be able to achieve a good match now that we have a different termination. The procedure is completely identical to what we've just done, so it's really no point in repeating it. So the values that we've calculated are 24.6 for this inductor, 16 for the other series inductor, and 2.46 for the capacitor. So the first thing that we need to do is to verify that these values are correct and that I am indeed getting a good match at the frequency of interest. So let's go to project options, select single point yet again and a frequency of 1 GHz, click on apply and then OK, and then simulate. Now if we go back to our Smith chart, we should be right in the center of the chart, which is where we want to be. So the matching network that we've got on the schematic is providing us with the match that we require between a 50 ohm source impedance and a 20 ohm load impedance. As I said, this was worked out with a very similar procedure to the one that we went through earlier. Now I can add a new circuit schematic. We'll call it Tmatch, and in this schematic we'll replicate the circuit that we had before, which produced a good match for us with the two elements. So again we'll have two ports here, port 1 which represents my source impedance, and then port 2 which represents the load impedance, so we'll change this to 20 ohm, and then we'll put a capacitor in shunt and an inductor in series to create the L-section matching network topology that we had in the previous tutorial. We'll add a ground reference and then we'll change the element values to what we had before, 3.9 picofarads and also 3.9 nanohenries. Again, before we do anything else, we need to check that this is indeed providing us with a good match. So we can go back to the Smith chart, right click on the chart, select add a new measurement, and then we'll select S11 for the schematic L-match. Click on apply and then OK. Then simulate. You can see that yet again, well, you can't see it so clearly, but yet again we are in the middle of the chart, right in the center, which means that we are providing a good match. Now, to see the frequency response of both networks, we first have to go back to project options, and then we have to select a frequency range which is suitable for our frequency response. As before, we'll deselect single point, select 100 MHz as a start, 4000 as an end, click on apply and then OK. Now if we go back to our rectangular graph here, where at the moment we've got the S21 in dB for the schematic Tmatch, we can add a second measurement, which is the S21 for L-match, and this way we can compare the two frequency responses. We need again to select the dB box so that both are displayed in the same units and have a comparable representation. Click on apply and then OK. Now simulate. Now let's get rid of the marker here. You can see that we've got a different, very different response from the two networks. First of all, the L matching network has got a relatively flat pass band for lower frequencies, so it's really quite a good low pass filter, whereas the T matching network has some considerable attenuation in at the lower frequencies, and hence is not really acting as much as a low pass but more as a band pass. Then also you can see that the slope of the frequency response is much sharper in the T matching network as opposed to the L. So outside the band of interest, the T matching network really attenuates the unwanted frequencies a lot more than the L section matching. So although it is more complex in terms of its design and topology and perhaps more expensive, it also gives some considerable performance advantages.